Okay, in this lecture, we're going to be going over assumption testing, more specifically hypothesis testing and assumption testing with hypothesis testing. So every single test that we have, every single hypothesis test that we run, there are assumptions that are associated with that hypothesis test. And it's really important that the data that you're using meets those assumptions before you can run that test. If your data does not meet those assumptions, then you cannot run that test. So it's essentially, a standard saying, hey, your data must meet this standard in order to be able to be used in this particular analysis. And if it does not meet this standard, then you need to do something else. So if your data doesn't meet the assumptions associated with a particular test, then the assumptions, or rather the results, or the results from running that test are not valid. So for instance, if I were to, just to kind of give you an example of what this is similar to, if I were to go on and say, hey, I'm going to drop a bowling ball from 10 stories up. Gravity has rules. The ball is going to accelerate at a rate of 9.8 meters per second, and it's going to keep on accelerating at that rate until it hits the ground, until it hits terminal velocity, one of the two. And so if I say, hey, how long is it going to take for a bowling ball to hit the ground? You're going to use that formula and say, hey, this is the formula. According to this formula, it's going to take this long to hit the ground. However, if I were to tell you that I actually dropped it from 10 stories up, but I dropped it on the moon, that changes everything. Now it no longer follows those exact same rules. Now I have to apply a completely different set of rules. In the same situation, if I were to say, hey, we're going to run this hypothesis test, but in order for us to run this hypothesis test, we need to make sure that the data already follows, or the population data follows, a normal distribution. But if the population data actually follows a uniform distribution, it's the same thing as saying, oh, I'm going to drop the ball on the moon as compared to I'm going to drop the ball on the earth and expect them to have the exact same results. You can't do that. You've got to make sure that you have met the right assumptions for your data before you run a test on it. And if you don't meet those assumptions, your data is useless. And the problem is that we see this all the time. All the time. There are countless situations you'll see people running these tests and saying, hey, this is what the data says. I've run this test, and according to my interpretation of this test, my interpretation of running this test on this particular data, these are the results. But if they don't run those assumptions, those results are completely useless. So in this particular unit, we're going to be going over 5 different tests. There's the single sample, independent samples, paired samples, chi-squared goodness of fit, and chi-squared for unequal proportions. And every single one of them has a different set of assumptions. And in this particular PowerPoint, we're not going to go over all of them because it wouldn't mean much to you right now because we've only gone over one test so far. But in this PowerPoint, every single one of the assumptions is listed. And so I'd encourage you to take a look at these assumptions as we're going through all of the different tests. Also, another thing to note is that the more complex a test is, more often, the more complex the assumptions are. So, for instance, if I run something called a Mancova, a Mancova has a lot of different assumptions, and the data has to be very specific in order to run this particular analysis called a Mancova. And a Mancova is really great. It provides you a tremendous amount of insight, but it's very complicated, and the data's more or less got to be perfect. And if it's not perfect, you've got to do a lot to it in order to be able to really understand and interpret the results. And so oftentimes the more complex a test is, the more perfect the data has to be, and the more at risk you are for actually having a bad interpretation of that data. So if you can have and run tests that have fewer assumptions, and you make sure that your data definitely follows those assumptions, you're going to be a lot better off, and your interpretation is able to be a lot more straightforward. So what happens if you violate an assumption? Well, first, before we do this, let's take a look at some of the assumptions. This right here, a single sample assumption. These are the assumptions for running a single sample test. Assumption number one, you can only have one dependent variable that is measured at the continuous level. Now, a single sample test, we have a single sample of a particular variable. So let's say, for instance, we're looking at everyone's height in the class. And that is a single, one dependent variable, everyone's height in the class, and it is the individual's height in my class compared to everyone in the entire population of Baylor. So I've got one dependent variable, which is any individual's heights, and it's measured at the continuous level. The next one is data. The observations are independent. In other words, one person's height in my class does not influence, somebody else's height in my class. All of the events are completely separate, completely independent of each other. So every single person's height contributes or is completely independent and is not influenced or does not influence anyone else's height. Also, there's no significant outliers in the two groups. So for instance, you have the population that doesn't have significant outliers, and if you have a significant outlier in my class, like for instance, in my first hour, I've got an individual who I think is like 6'6". He might be an outlier, he might not, but if you have a significant outlier, that's something that you've got to pay attention to and make sure that you're aware of that before you continue, and you might have to do some work to it. But you can't have any significant outliers. Next, dependent variables should be approximately normally distributed for the population as well as for the single sample. And so if it's not approximately normally distributed, then that's an issue, and you've got to take a look at that and really make sure that you've got that that you understand how it's distributed, and so coming back to this, so if it's not perfectly normally distributed, it might be uniformly distributed, it might have a different distribution, and you might need to run a different test for that, which brings us to what happens if I violate an assumption. So for the single sample that we just saw, there are four different assumptions. There are four different assumptions, and for each one of those assumptions that you have, you might, if you violate it, you still might be able to use that particular test, but you may need to do some work to the data in order to be able to make it work. First of all, right here, if you violate assumption one says one dependent variable that is measured at the continuous level. This one right here, you have to have this in order to run a single sample test. If you are dealing with a dependent variable that is categorical, that is discrete, then you're going to have to run a different test completely. So assumption one, in this particular situation, you can't even run a single sample. The results would be all wrong. So next, assumption two, if you violate this one, the observations are independent. So in other words, the observations are dependent on each other. So if one is dependent on the other, you might need to run a different test as well, where you run a paired test, a paired samples t-test or something to that effect. So if they are dependent on each other, you're also going to have to run a different test. For assumption three, there's no significant outliers in the two groups if the independent variables in terms of the dependent variable. So in this particular situation, what this is saying is there's no significant outliers. There might be a situation where you have somebody that's really far outside. And if you only have one person, it's possible that you might be able to just remove that one person and say, we ran this test and removed this one individual from this test. Which I would not necessarily say that that's a great idea, because there might be a reason why that person is in there or that observation is in there. Another situation is when you have data that is bimodal. So you've got two groups that are represented in a particular sample, and you've got one high and one low, and it's just not normally distributed. A lot of times, what you can do is you can actually look at just one of those two groups and say, hey, we're going to look at just this one group and see if this one group is normally distributed, or if this one group is normally distributed. And what you actually do at that point in time is you say, hey, we're going to redefine who we're looking at, so that way we can run this test appropriately and get good insight. And then another thing that you can actually do is run transformations. You can run log transformations. You can run all sorts of different transformations to the data to be able to take data that is skewed, or that is bimodal, or that is just not normal, and you can transform it to being normal, which you'll learn a lot more about hopefully in QBA 2. And then lastly, same thing with this, the dependent variable should be approximately normally distributed for each group of the independent variables. And same thing, you can run transformations if it's not normally distributed, or redefine your criteria for the inclusion or exclusion. And last but not least, you may just conclude that it's not possible to test your data. If your data is really bad, it may just be that you cannot test your data. And so I'm going to page through right here. We've got the single sample assumptions. Right here, we've got the independent sample assumptions. We've got the paired sample assumptions, and goodness of fit for equal expected frequencies, and goodness of fit for unequal expected frequencies. Now, as I go through each one of these tests in my lecture, I will go through these assumptions during these actual tests. And so I'm not going to go through them all right now. I'm only going through one. But what I want you to take away from this is that every single one of these tests has assumptions, and you have to check the assumptions to make sure that your data is the appropriate data and is behaving appropriately before you run the test. If you don't test the assumptions, your findings are worthless. Absolutely worthless. Because once again, it's like saying, hey, my my car is 27 long. 27 what long? 27 feet long, 27 meters long, 27 inches long. We don't know. 27 hand lengths long. When you don't have when you don't meet the assumptions, it's like you are functioning without an appropriate standard. And so you've got to meet that standard of assumptions before you run your test, because if you don't meet those assumptions, your findings are completely worthless. Thanks so much. Hope this was beneficial. There is no worksheet for this particular one. I might put some notes down below just for you to follow along, but that's pretty much it. Appreciate y'all.